Hi everyone, welcome to Stats Rescue 911. My name is Lynn, and in this video session, we're going to learn how to tell the difference between a correlation versus a dependent t-test versus a chi-square contingency test. The reason I'm covering this is because very often students choose the incorrect test. These three are easily confused, so I want to spend a few minutes talking about how to figure out which one you should be using. All right, so before we get started, it is pretty important you need to know something about each of these tests. So if you've never heard of correlation before, if you've never heard of t-test or the chi-square test, then you really shouldn't be watching this video. You need to know something about each of these tests in order to tell them apart. All right, so if you need to, go back to some of my previous videos and watch those, and then come back to this one. All right, so first let's look at the difference between correlation and a dependent t-test. Here we're looking at Pearson correlation, so we're looking at scores and we're trying to determine if there's a linear relationship between those scores, versus a dependent t-test where you have one independent variable with two levels and the same people are tested in each level. All right, so let's look at where the confusion comes in. First and foremost, the dependent t-test is also called the correlated t-test. So that likely has is a big reason why some people confuse them, because correlation, correlated t-test, it does sound very, very similar. All right, but let's look a little deeper and look at what each test is trying to accomplish, okay, and how the data are set up, okay, because I think that is where a lot of the confusion comes in. So let's start here with correlation. If you're doing simple correlation, that means you're going to have two sets of scores. You're going to have a set of data, a set of scores for X and for Y. All right, so you have your X scores here and your Y scores over on this side. Now, each person has a score for X and a score for Y. So whatever score this is for one person, okay, Dr. X, and this is the second score for Dr. X. So each person contributes two scores, one for X, one for Y. All right, same thing here. These two scores would come from the same person. All right, Dr. J, and then these two scores come from the same person, etc. All right, so this is the setup for the correlation. Excuse me. All right, now let's look at how it's set up for the dependent t-test. All right, we also have two sets of scores. See where some of the confusion's coming in? We have two sets of scores, one for level 1, one for level 2. All right, so so you have an independent variable with two categories or levels. So here are all the scores for level 1. Here are the scores for level 2. All right, and each person contributes a score for 1 and a score for 2. So these two scores come from the same person, whoever I said before, Dr. X. These two people these two scores come from the same person, Dr. Y. These two scores come from the same person, Dr. J, etc. Okay, so if we just look at the way the data is organized, it looks very, very similar. Here we have two sets of numbers, and each pair comes from one person. Here we have two sets of numbers, and each pair comes from the same person. So, so far, it's easily confused. But here's where the differences lie. First of all, if we look at correlation, X and Y are two separate variables, like height and weight, time spent studying, test grade, age, and the number of hairs on your head. All right, these are two separate variables. All right. If we go over here for the t-test, level 1 and level 2 are two categories of the same variable. All right. So let's say we wanted to know if method of instruction has any effect on test scores. So you have online versus face-to-face. These are two categories of the same variable, method of instruction. So that's one difference, okay? Again, two categories of the same variable versus over here, two different variables. Now, here's another difference. With the t-test, we want to know if method of instruction had any effect on test grades. So these numbers here are all test grades. All right, these are all test grades. And over here, these are different variables. So this might be height in inches, and this could be weight in pounds or kilograms. You see how these are not the same unit of measurement necessarily? All right, whereas here, it's the same unit of measurement. It's the same variable, test grades, test grades, test grades, test grades, all right? What's another difference? Well, with the dependent t-test, in order for you to know if method of instruction had any effect on test grades, you compare the two means, the mean for level 1 to the mean for level 2. That's what is being compared by the t-test. It's the means that are being compared. When you run a correlation, you don't calculate the means. Why would you? If you want to know if height and weight are related to each other, would it make any sense to calculate the mean height and compare it to the mean weight? It really wouldn't. All right. So here with correlation, you are not looking at means. Over here for the t-test, you are looking at means. All right. So again, for the t-test, you're comparing the means to see if method of instruction has any effect on test scores. So these are all test scores here. All of these numbers, same variable here. Okay. The different groupings, well, those are two different categories of your independent variable. These are your dependent variables, okay? All right, over here, the question you're asking is different. You're not going to compare the two means. You want to know what happens to scores on, say, variable y when you change scores on variable x. So as x increases, what happens to the scores on y? You're not interested about having anything to do with the means. Not at all, okay? So let's look at an example here. Oh, I'm sorry, I did the example. It's late in the day. Let's look at how the correlation is answering a different question from the t-test. All right, so the correlation is looking for relationships between two different variables, x and y, and it does that by looking at their scores. So is variable y related to variable x? We're going to look at scores for each, and they are two separate variables. Now, the t-test is looking for differences among means. All right, so the t-test is going to compare the mean for level 1 to the mean for level 2. All right, and the data, if we remember, if we go back, let me just remind you, the data here is not from two different variables. This data is all from the same variable, test scores. These are all test scores. All right, okay. So let me show you that relationship and differences among means are not the same thing. So over here, we have two sets of data, right? We have x and y. Or you could think of it as this is level 1, this is level 2. Now, if it was level 1, level 2, and we wanted to know if the means are different, we would compare these means, the mean for level 1 and the mean for level 2. And here the mean is 2.5. Here's the mean for the next level, 2.5. We can easily see that these two means are not the same, are the same. All right, so if we were to run a t-test On identical means, we would see the t-test is not significant. But if we were to look at the correlation of scores on X with scores on Y, now remember, these are two separate variables. If we plotted that out, we would get a perfect correlation, +1, all right, in this case. And so R, the correlation would be significant, but T would not, all right? Why is that? Because they're looking at different questions. The correlation is asking questions about the relationship between scores, and T is looking at the difference between means. Those are two different questions. Here's another possibility. Here we have variable X, variable Y, or this could be level 1, level 2. If we consider this to be level 1 and 2 and look at their means, now we see a striking difference between the means, 2.5 versus 25. So that opens up the possibility that we will get a significant t-test with means being different. Okay, so that's a possibility. But if you look at the correlation, all right, what would you find? Well, once again, we see that the points here in this case would all fall on the same line, so we get a perfect correlation, and so R would be significant. So right away, we're beginning to see that one test tells you nothing about the other test. Here, R is significant, but the T is not. Over here, R is significant and T is significant. And look at all these remaining possibilities. Here, the difference between the means would be not significant. T is not significant. And if we plotted the XY pairs, we would see that the correlation is right around 0. So the correlation would not be significant. And then finally, if we compared these two means, we would say, hey, look, it's quite likely that we'll get a significant T value. The means are very, very different. So T might be significant. And if we plotted the XY pairs, we would again see that the correlation is not significant. So you see how any combination is possible. Here, R is significant, T is not. R is significant, T is significant. R is not significant, T is not significant. R is not significant, T is significant. So one test, depending, you could get a significant or a non-significant result on that one test. Let's say it's correlation. It's going to tell you nothing about whether the t-test would be significant or not. All right, and that's because they are looking at two different questions. Now, I did this so that you would understand that looking for differences among means is not the same thing as looking at scores. Just remember, in reality, if this was height and this was weight, in reality, I don't see why you would want to compare the mean height to the mean weight. All right. I am just showing you this just to help you see that correlation asks questions about scores, dependent t-tests ask questions about means, and these are two separate, unrelated questions. Okay? All right. Now, let's move to the next source of confusion. A lot of people confuse the correlation, Pearson correlation, with the chi-square contingency test. All right? And it kind of makes sense because if you look at the chi-square and correlation, they're both asking questions about relationships. Is A related to B or is B related to A? But they're doing so in different ways. All right? So if we look at correlation, correlation is going to analyze scores from two interval or ratio variables. This is a key here, two interval ratio variables, numerical variables. Chi-square analyzes frequencies from two categorical variables. So here we see two differences. Correlation is working with scores. Chi-square is working with frequencies. That's one difference. The second difference, Correlation looks at interval ratio variables. We're looking at Pearson. So it's looking at interval or ratio variables, and chi-square is looking at categorical variables. All right, so let's look at an example. Here we have the data set up to look at a correlation between scores on X and scores on Y. So remember, these are two different variables. So X could be the time you spend studying, and Y could be test scores. All right, so these are from the same people, right? You have to remember that. So this is, let's say this is your friend, studies 1 hour and gets 58%. You study 4.2 hours and get 95%. So you see how these are lined up in pairs, so each pair belongs to one person, all right? So if we wanted to see if X and Y are related to each other, we would run a correlation, and that correlation would look at the scores on X and the scores on Y, and it would determine whether there are reliable changes in X that predict changes in Y. So as X increases, what happens to the Y scores? All right. Now, that would tell us if there is a relationship or not in the scores. Another way of asking the question, though, could be to set it up as a chi-square contingency test. But notice the difference. We still have one variable here. Here's the amount of time you spend studying. And here is the score on the test. So that resembles this over here. But look, this here has not been categorized. These have not been placed into any kind of categories. 58, 60, 88, they're not grouped. Same thing with the X scores, they're not grouped. Over here they are. We've taken people's study time and put them into one of three groups. So either 0 to 1 hour spent studying, 1.1 to 4 hours, 4.1 or more hours. All right, see how the variable's been categorized? Same thing with test scores. Over here, test scores were not grouped. Over here they are. We group them 0 to 59, 60 to 79, 80 to 100. All right? Now, importantly, with correlation, we look at scores. But now with chi-square, we're actually going to look at frequencies. So this represents the number of people falling into this category. So those people who studied between 0 and 1 hours and got 59% or less. Over here, this is the number of people who studied between 1.1 and 4 hours and scored, I lost my cursor, come on, scored between 60 and 79%. Okay, so it's the number of people in that category combination. Over here, this would be the number of people who scored between 80 and 100% and studied between 0 and 1 hours. All right, so we're going to be able to determine if there's a relationship between the time spent studying and test scores, but we do it differently. Here, we're looking at frequencies. Over here with correlation, we're looking at scores. With correlation, we have two variables, X and Y, that are not put into groups or categories, right? This is not categorized, neither is this one. But over here, we take each variable and put people into groups or categories, right? And then we count the number of people in each combination. All right, so I hope that clears up some of the confusion between these three tests, the correlation coefficient or Pearson correlation, dependent t-test, and chi-square contingency tests. And I hope you like this video. If you do, hit that like button and watch some of my other videos. All right, see ya.